Welcome all at the TCS seminar at Jagiellonian. Today we're happy to meet in the room. We have a local speaker, local guest, Clément Rambaud from Université Côte d'Azur. Clément was our visitor, our intern last year. We spent here five months, something around this. We had a very nice project together. Now Clément already started PhD on the supervision of Frédéric Ravet in Nice. And I imagine that you will talk about, this is with Frédéric, this work? Yes, it is. So some initial work within your PhD program. It's great that you came here again, Clément. The floor is yours.
Thanks for the introduction. Okay, so I will talk about inversions in oriented graphs. So this is a joint work with all these people. And okay, so what is this notion of inversions? Maybe I just, no. Okay, I don't know if I can remove it. Okay,
this should
anyway.
Disappear somehow, sooner or later.
Okay. Okay.
Disable chat.
Disable. No.
Oh yeah. So
okay.
click there, then close it. Maybe.
Okay.
Maybe now.
Okay, perfect. Now I can just put it. Okay, sorry. So, okay, so what is this notion of inversions in an oriented graph? So you take an oriented graph and a set of vertices, a set X, and what I call the inversion of X is the reversal of every edge with both endpoints in X. Okay, so I reverse the arcs of all the arcs of the subgraph induced by X. Okay, so this is something more general than just reversing the orientation of one arc. Okay, because now we can reverse the orientation of a lot of arcs in one step. Okay, and this gives a notion of distance between two orientations of the same undirected graph. Okay, so if G1 and G2 are two orientations of the same undirected graph, the distance between these two orientations is the smallest integral t, such that there are t sets of vertices, x1 up to xt, such that when I inverse x1, so I reverse the orientation of all the arcs with both endpoints in x1, then I do the same for x2, then etc. the same for xt. At the end, I obtain g2. Okay, so this is the notion of distance between orientations. Okay, this is kind of reconfiguration problem of orientations of an undirected graph, of orientations of an undirected graph. And we investigate three main questions. So the first one is how to make an oriented graph acyclic. Okay, so we have an oriented graph and we want to make it acyclic. And we have this operation that we can perform, and we ask how many inversions I need to make in order to obtain an acyclic, directed acyclic graph. Okay, so this is a first question. A second question will be somehow the opposite. So how to make it k-strong? So k-strong here it means k vertex strongly connected. Okay, so when you take two vertices, there are k internally vertex disjoint paths between them, directed path. Okay, so this is somehow the opposite. And then the third question, which is maybe the most natural one, actually, what is the maximum distance between two orientations of a graph? Okay. So let's start with the first question. So how to make an oriented graph acyclic? So actually, we mostly look at the maximum value of this parameter that I call inversion number of G, which is the minimum distance to any acyclic orientation. And I will look at the maximum of this parameter over all n-vertex-oriented graphs. Okay, and actually, this notion of inversion was defined in a paper where they investigated this question and they gave this estimation. So the upper bound is at most n minus 4, and the lower bound is n/2 minus log n minus 4. Okay. And so the proof was quite simple. So the upper bound comes from the fact that when you add one vertex, you increase by at most one this parameter, and the base stays if u is -4. Okay. And the lower bound was a counting argument. So I reformulated this in terms of probabilities. So draw a tournament uniformly at random, okay? And we upper bound the probability that it has inversion number at most t. We bound the probability that there exists t sets of vertices, so that if you inverse each of them, then you will obtain an acyclic oriented graph. So a tournament here, it's an orientation of a complete graph, okay, on n vertices. And I draw every edge uniformly at random. Okay, the orientation is chosen at random independently. Okay, so how to upper bound this probability? Well, you do just a union bound. So the probability that there exists a T such set that most the sum over all such sets of the probability that the resulting tournament is acyclic. Okay, so how many choices we have for the set? It's at most 2 to the n to the t, so 2 to the n t. Okay, and now if the inversions are fixed, the result is just a random tournament. Okay, and the probability that a random tournament is acyclic is the number of acyclic tournaments divided by the number of tournaments. And so this is n factorial divided by 2 to the n to 2. And this probability is smaller than 1 if t is smaller than n minus 1 over 2 minus log n. Okay, so in particular, there exists a tournament such that the inversion number is larger than t. Okay, and so our first contribution is a better estimation of this function. So we prove that it's at most n minus log n, which is better than n minus 4. And for the lower bound, at least n minus big O of square root of n log n. So this is really close to n. Okay. And yes, just one remark. Almost simultaneously on arXiv, another paper appeared with the same theorem and the same proof. So if you want another writing of the proof, here is one. Okay. So first, the upper bound. So first, we show that two orientations are always at distance at most n minus 1. So in particular, you can reach one which is acyclic with at most n minus 1 inversions. Okay, and here the algorithm is quite simple. Pick a vertex, V1, and your first inversion will be V1 union its in neighborhood. Okay, so when you do this inversion, now V1 dominates every other vertices. Okay, so that's a source, and now you recurse on the resulting tournament minus V1. Okay, you continue like that. And so this gives, at the end, n minus 1 inversions. But what is important is that here we can actually reach any orientation doing that. Because, okay, here you can take V1 and all the other neighbors which are badly oriented with V1. Okay? This gives your first inversions. And when you do that, now all the edges incident to V1 are in the orientations you wanted. So you're happy, and then you can recurse on what you made. So actually, with this method, you can reach any orientation in n minus 1 inversions. Okay. Okay, so now our goal will be to find one inversion at distance, one acyclic orientation, sorry, at distance at most n minus log n. Okay. So how to do that? Again, we pick arbitrarily a vertex V1. And either it's out degree or it's in degree is at most n minus 1 over 2. So let's say it's in degree. Okay, so the case is same. Now what we do is that we will apply the algorithm of the previous slide by starting with vertices of the in neighborhood of V1. So you add them one by one. Okay. And what happens is that at the end, when you will process all these vertices, you will have something acyclic here, and all the arcs from this set to the other vertices are leaving. So here, all the arcs are from here to here. Okay. And so in the algorithm of the previous slide, at this step, we should do something for V1. But here, actually, we have nothing to do because the edges are already in the right direction. If we want to apply induction on this, V1 is already a source in this subtournament. And so we skipped one inversion compared to the previous method. Okay, so every time we multiply by 2 the number of vertices, we are able to save one inversion compared to the previous method. So this gives this n minus log n. Okay. Okay. So now let's prove the lower bound. So the goal is to prove the existence of a tournament on n vertices, such that you need at least n minus a small of n inversions to make it acyclic. So the proof of this fact relies on an argument of rank of linear algebra over the field F2 with two elements. So this is the field with two elements, whereas the sum is modulo 2. Okay. And to illustrate this method, we'll first show that there are two tournaments at distance at n-1. Okay. So these two tournaments will be first TTN. So TTN is a transitive tournament of order n. So an acyclic tournament. You fix one acyclic tournament. And the other tournament that will be very far away from this one will be Tn, which is obtained by reversing an Hamiltonian path. So all the three edges now are from right to left. Okay. And now we'll show that these two tournaments are at distance at least n-1. And actually exactly n-1, because we proved earlier that two tournaments are always at distance at most. Okay. So here, one thing which is really important is that the tournaments are labeled. So here, when I say TTN, it's really one fixed acyclic tournament. Because otherwise, we proved that before that you can reach one acyclic tournament with n-log n inversions, but here we fix the one we want to reach. Okay, so how to prove that? Suppose for contradiction that you have T inversions, x1 up to xt, that transform Tn into Ttn. Okay, so you apply your inversions, x1 to xt, and at the end you obtain Ttn from Tn. Okay, so we represent every inversion xk as a matrix. So this matrix will be mk, and it's an n by n matrix where the cell ij is 1 if and only if both vi and vj are in xk. So v1 up to vn is the topological ordering of your acyclic tournament. Okay, and the cell ij is 1 if both vi and vj are in your inversion and 0 otherwise. Okay, so this is a kind of square of 1 inside a matrix, and this is a 0-1 matrix. So the other vertices are 0 because we work over F2. So if it's not a 1, it's a 0. Okay, so now what is very nice is that this matrix MK describes exactly which arc are reversed by XK. Okay, if you want to know if VIVJ is reversed, you look at the cell ij. If it's a 1, then yes, it's reversed because both endpoints are in the set xk. And if it's a 0, no, it isn't. Okay. So now when we sum these matrices, okay, the cell ij is 1 if and only if the arc VIVJ has been reversed an odd number of times. And so this means that it has been reversed. Okay? Because when you reverse a matrix twice, you come back to your original position. Okay, so we know what is this sum of matrices. Okay, M1 plus etc. plus MT. This is a matrix M, and we know every cell except the one in the diagonal. Okay, so this is something like that. Okay, and this 0 and 1s comes from the fact that we choose our pair of tournaments by reversing the Hamiltonian path, so we obtain something like this. Okay, but now this is the sum of T matrices of rank 1. And such matrix have rank at least n-1, whatever the value in the diagonal. And so T is at least n-1. Okay. Okay, so this is how this rank argument works. And now our goal will be to find a lower bound to find a tournament far from any acyclic tournament. So the solution is to take it at random. So you take a tournament T uniformly at random, and we put that with positive probability, its inversion number is larger than n minus constant times square root of n. And the constant is 2 or square root of 2. So what is the proof? So let's bound the probability that the inversion number of t is at most n minus r, so r will be roughly square root of n. So what is this probability? It's a probability that there exists one acyclic tournament T prime at distance at most of n minus r. Okay, so here we do 1 union bound on this acyclic tournament T prime. There are n factorial of them. Okay, so here. And now the acyclic tournament is fixed. Okay, but now we know how to bound the lower bound the distance between two tournaments using this idea of representing our inversions in the matrix. Okay. And so actually this probability is at most the probability that a random symmetric n by n matrix has rank at most n minus r. Okay, just doing the same reasoning as before. Okay, because if there are n minus r inversions going from T to TTN, then we can represent them in a matrix, and this matrix should be exactly the adjacency matrix of T. Okay, and this is a matrix which is random, and the probability that the rank of a random symmetric n by n matrix is at most n minus r. You can show that this is at most 2 to the minus r squared. So here there is a 2 to the n because of the value of the diagonal, but it doesn't really matter for us. And now, if r is of order of square root of n again, this probability is smaller than 1. So there is a tournament that you cannot make a cyclic with less than n minus square root of n log n. Okay, so just a small open problem is to find the constructions achieving this bound. So the best constructions is n over 3. So we have a complete construction of tournaments at distance at least n over 3 for many cyclic oriented graph. This is very far from this n minus small of n. It would be nice to have better construction. Okay, so now let's move to the second question. So the second question is how to make a tournament k vertex strongly connected. Okay, so here strongly connected, it means that when you take two vertices, there are k vertex disjoint paths between them. Okay, so I will only focus on tournaments here again because for oriented graphs it's more complicated. And one observation is that we need the number of vertices n to be at least 2k plus 1, because otherwise can't make it strongly connected. Okay, so now if the number of vertices is at least 2k plus 1, we can define this parameter, which is a k strong inversion number of T, which is the smallest number of inversions I need to make it k strongly connected. Okay. And to prove bounds on this, our main tool will be this lemma, which says that if you have a k-strong digraph and you add a new vertex with in degree and out degree f is k, then the resulting digraph is also k-strong. Okay. This is, I think, not natural. Okay, you add a vertex with a lot of neighbors, and it's still k-strong. Okay. So using this, we can show that if T is a tournament on at least 2k plus 1 vertices, then you can make it k-strong using at most 2k inversions. And here I will just sketch the proof. You select a set of 2k plus 1 vertices arbitrarily. This will be a core in your tournament, and you will make it k-strong using 2k inversions just by doing what we were doing at the beginning. Okay, you can reach any inversion, any orientation of an n-vertex graph using n minus 1 inversion. So here you can make this sub-tournament k-strong using 2k inversion. And now the idea is that if we place the other vertices outside this set carefully in the right inversions, then at the end, every vertex outside this core will have at least k in neighbors and k out neighbors inside this set. And so in total, the tournament will be k-strong. Okay, skip the detail, but that's the idea of the proof. And by a counting argument, you can show that there are tournaments on 2k plus 1 vertices that needs at least log k inversions to be made k-strong. And so here we have a big gap, which is also an open problem. We tried to fill this gap, but we didn't manage to improve these 2 terms. Okay. Maybe something more surprising is that if you have a tournament which is really large, so really large means at least split, then you can make it k-strong using 1 inversion. Okay. And here, the proof is a bit similar, actually. You will build a sub-tournament which will be k-strong, and then you will manage to make all the other vertices, to make all other vertices such that they have at least k in neighbors and k out neighbors on this smaller sub-tournament. And so in total, the tournament will be k-strong. So how to do that? Well, it's just because a big tournament will contain 3 sets, A, B, C, of size k, 2k minus 1, and k, so that we have something like this. So A dominates B union C, so really you have every arc between A and B going from A to B, and etc. The same for B and C, and the same for A and C. Okay, and now what you do for your first inversion, you take A union C. Okay, so now we will have something that turns like that, and this will be k-strong. This will be your core of tournament, which will be k-strong. And now what is nice is that when you take a vertex outside, either at the beginning it has already k in neighbors and k out neighbors in this set, or if it doesn't, when you put it in the inversion, it will have at the end k in neighbors and k out neighbors in this. So again, by the same argument, with a single inversion, you make it k strong. Okay, and actually you can really improve this bound because just if you take n at least 19k minus 2, then there exists such an inversion making it k strong, but the proof is more. Okay, and if your goal is really to have the best possible bound here, doing some probabilistic arguments, you can show the following. For every epsilon positive, if n is at least 2 plus epsilon k, then you can make it k strong using at most a function of epsilon inversions. So here, just if you want to have a constant number of inversions, but to have really a better bound on the number of vertices, you can. Okay, and the proof is basically by drawing the inversions at random, and you will obtain a graph which is a tournament which is not far from being a random tournament. Not really, but not too far. Okay, so now when we move to the third question, which is maybe the most natural one actually, which is how far two orientations can be if I fix my underlying graph. Okay, so I fix a graph G, and now formally we can define the inversion graph of G, which is the graph whose vertices are orientations of G, and two orientations are adjacent if you can go from one to the other using one inversion. Okay, so now really the distance between orientations are really distances between vertices in this graph. Okay, and now we look at the diameter of this graph. Okay, it is the maximum distance between two orientations of G. So just first, the clique on n vertices, this parameter is n minus 1. Okay, so we proved that it's at most n minus 1 at the beginning. We proved that you can reach any orientation of an n vertex graph using at most n minus 1 vertices. So this proves that this vector is at most n minus 1. And it's at least n minus 1. This was the proof when we found two tournaments at distance at least n minus 1 using this strong argument. Okay, so the clique has a inversion diameter exactly n minus 1. So now we focus on sparse graphs for which this parameter is bounded. Okay, so for trees, it's at most 2. We'll see later why. And it has a nice application. And in particular, this will imply easily using known tools that for planar graphs, this is bounded. Okay, and actually you can even get this bound. So when you take two orientations of the same planar graph, you can go from one to the other using at most 12 inversions. Okay, you can find 12 sets transforming one into the other. And more generally, we have a characterization of graph classes with bounded inversion diameter in terms of already known parameters such as the acyclic chromatic number and the star chromatic number. I will explain it later. And for maximum bounded maximum degree, we have more precise bounds, which are 2 delta minus 1 and delta plus delta minus 1 if the graph is bipartite. And so we'll see how to prove it. Okay, so let's start with trees. Okay, so the goal is to find, given two orientations of the same tree, two sets of vertices, that if you inverse one and then the other, you go from one orientation of the tree to the other one. Okay? So actually, it's not really anymore a problem about oriented graphs. Okay? Now, if you fix your two orientations, you have two types of edges, the one which are oriented in the same direction in the two orientations, and the one which are not. So let's call red the edges which are not oriented in the same direction in the two orientations, and black the other ones. And here to prove that the inversion diameter of trees is at most 2, you will consider the connected the red components in your tree. And since a tree is bipartite, you can partition your set of red components in two sets which are independent. Okay? And so now what you do, you inverse the first set of red components. So now all the edges that were red here are now black because they are in the good direction, okay, in the same direction in both rotations. And now you inverse the other set. and that's it. You found your other orientation. Okay. So this simple lemma has a very nice consequence, which is that the inversion diameter is bounded by a function of the acyclic chromatic number. So okay. Okay, so you have the edges which are red, which means that they are not in the same direction in your two orientations, and the black, which are the other ones. So you have the red components. So if you want to do it formally, contract this red components. Now you have your tree of, and remove the vertices which are incident to no red components. And now you have a tree of red components, which this graph is bipartite. So you have a bipartition of the red components, which are independent between them. And now your first inversion is the union of the first color class of components, and then the other one. That's all. So here you do these two components, okay, and then the other one. We see another proof of this later using another argument. Okay, so this simple lemma has a nice consequence. So first, I need to define the acyclic chromatic number. So the acyclic chromatic number of an undirected graph G is the minimum number of colors in a proper coloring of G, such that when you have a cycle, you must have at least 3 colors in this cycle. So every cycle has at least 3 colors. So another way to say it is to say that the union of 2 color classes must induce the forest. Okay. And so in particular, the H set of G can be partitioned into acyclic chromatic number G choose 2 induced forest. Okay, every pair of colors gives an induced forest, and this is a partition of your H set. So now, if you want to apply it to bound the inversion diameter, this is quite simple because now you have this partition into induced forest, and so you inverse each of these forests one by one. And since that's induced forest, okay. So this proves that the inversion diameter of G is at most 2 times acyclic chromatic number choose 2. Okay, so in particular for planar graphs, since we know that planar graphs are 5 acyclically colorable, this proves that the inversion diameter of planar graph is at most 20. Okay. And what is maybe more surprising is that actually not only the inversion diameter is at most a function of the acyclic chromatic number, but the acyclic chromatic number is at most a function of the inversion diameter. I'm not sure the proof now. But it uses the fact that the acyclic chromatic number is known to be tied to some other parameters like the star chromatic number. So now you want that the union of 2 color classes induces a star forest instead of just a forest. And also the oriented chromatic number, which is slightly different, but behaves the same. Okay, so this gives a complete characterization of graph classes having bounded inversion diameter. So namely, a graph has bounded inversion diameter. A class of graphs has bounded inversion diameter if and only if it has bounded acyclic chromatic number. Okay. And yes, that's it. So in particular, graphs of bounded maximum degree have bounded inversion diameter. So, and now we will try to obtain the best bounds for this. Okay, so let's start with an easy argument, which proves that it's at most the maximum degree squared. So here, the proof is almost the same argument at the beginning when we were adding vertices one by one. Okay, but now the observation is that instead of adding one vertex at a time, you add the full 2 independent sets. So 2 independent sets is a set of vertices pairwise at distance at least 3. Okay, and you can observe that if you have such a set, you can add it completely to your graph using one inversion. So you will resolve all the edges between this independent set and the other vertices in one inversion, and then you will recurse on what remains. And you can find the coloring of your graph with delta square minus 1 colors, such that every color class is a 2 independent set. So adding them one by one, you obtain this bound of delta square. Okay. Actually, we believe that this is always at most delta. And okay, we know that it's true for maximum degree at most 2, which are cycles and paths. And I check it to for cubic graphs on at most 14 vertices using a computer. And also for complete graphs, it's tight. For multipartite complete graphs, also it's tight. So yes, it's tempting to believe that this is always the case. And for bipartite graphs, we are not very far from it. We can prove that the inversion diameter is at most delta plus log delta minus 1. And for general graphs, we can show that it's at most 2 delta minus 1. And now I will explain how this two proofs works. Okay. So these two proofs relies on this observation, which is an algebraic reformulation of the problem. So the idea is that when you have two orientations of your graph, you have two types of edges, the one which are oriented in the same direction and the one which are not. Okay, so you can represent it by putting a 0 and a 1 on every edge. A 0 means you don't want to reverse it, and 1 means you want to reverse it. And now if you have a set of a family of inversions going from one orientation to the other, we can represent this set as vectors on every vertex. And the vector of the vertex u will indicate in which inversion this vertex is. Okay. So, for example, the coordinate I is 1 if the vertex u is in the inversion xi and 0 otherwise. And now what is nice is that when you look at an edge u and you compute the scalar product of the vector of u with the vector of v, then you get how many times the edge between u and v has been reversed. Okay. It counts how many times both u and v are in the inversion. And so now you're happy if and only if this scalar product is exactly what you were asking for. So it's exactly the 0 or the 1 that you put on the edge at the beginning. So more formally, the inversion diameter is the smallest integer t. So this will be the dimension of my vectors. This is also the number of inversions. Such that for every labeling C of the edges with 0 and 1, so this is again modulo 2. So that's elements of the field with elements. There exists a family of vectors to put on the vertices, so that the labels on the edges are realized as scalar products of the endpoints. Okay. So this observation is quite useful for us because now we can do some greedy algorithms to find our inversions. We'll find for every vertex its vector. Okay, and at the end we will find the okay. So let's start with an example. So this will be another proof that the trees have inversion diameter plus 2. So you start from the root and you will go from the root to the leaves. And every time you will choose a vector which is non-zero, such that the edge with the parent is satisfied, meaning that the scalar product with the parent gives exactly what you want. Okay, so let's start with a non-zero vector for the root arbitrarily, and then choose a child of the root. And now you take a vector such that the label here is realized as a scalar product of these two vectors. Okay, and then you can do that. Okay, and you can continue. And actually, it always works because when you want to find the vector for this one, for example, okay, you want to satisfy one linear constraint, which is this vector times this one gives 1. Okay, so this is a linear constraint. And it has a solution because this vector is non-zero. And so actually the space of solution is an affine space of dimension 1. And so it contains a non-zero vector, and so I can take it, and then I continue. Okay? So let's use this method to bound the inversion diameter of bipartite. So we'll show that it's at most delta plus log delta minus 1. Okay, so let T be this number of inversions, so the dimensions of our vectors. And let AB be the partition, the bipartition of the graph. So the proof will be in 2 steps. First, we'll find vectors for A and then for B. And for A, we'll find vectors such that for every vertex of B, the neighborhood of this vertex will give a family of linearly independent vectors. Okay? So why we want that? Because now the second step, that is finding vectors for vertices in V, will be quite simple, because if you have this property that all the neighborhood gives a family of linearly independent vectors, then you just have a system of linear equations to satisfy, and all these equations are linearly independent. And so the space of solution is an affine space of dimension t minus the number of constraints, and so it's non-empty. So you will find a solution for this vertex. So you will find the vector you want for this vertex. So we need to find vectors for A such that every vertex in B sees only linearly independent vectors. So this is just a greedy algorithm. So when we want to find the vector for AI, the only constraint we have is that for every neighbor B of AI, we need to avoid the space spanned by the other neighbors of B. Okay. So for every neighbor of AI, we need to avoid a space of dimension at most delta minus 1. And now, just by a counting argument, you have at most delta spaces of dimension delta minus 1 to avoid. Just by a counting argument, there is a vector which is in none of the spaces. And so you find it. And okay, so now I would like to show you another formulation of this result in terms of partial matrices and completion of partial matrices. So actually, your bipartite graph, you can represent it as a partial matrix. So the rows correspond to vertices in A, the columns to vertices in B. And now the cell ij is a star if there is no edge between the vertex I and the vertex j. Okay. There is a 1 if there is an edge and this edge has label 1, and there is a 0 if there is an edge and the label is 0. Okay. And now what we proved is that we can find vectors such that the scalar products gives exactly the values which are here, the fixed values. Okay. And now this gives a completion of this matrix, okay? Because even non-edges have a value if you want. You just take the scalar products, and this gives a value. And so this completes this matrix. And this completion of the matrix has a property that the rank is at most d plus log d minus 1, just because it's the product of two matrices of dimension something times d plus log d minus 1. Okay. And actually, in an infinite field, you can drop this plus log d minus 1. This is probably already more. But okay, because the counting argument becomes simpler because you cannot cover the full space with finitely many proper subspaces in an infinite field. So this plus log will disappear. Okay. So now let's move to graphs in general, not only bipartite graphs. And using the same method, we can prove that the inversion diameter of G is at most 2 times the maximum degree minus 1. And so now we just do the two steps simultaneously. So when you want to add a vertex, you will need to satisfy two types of constraints. First, the edges incident to this vertex will have labels that is realized as the scalar product of this vector with the neighbor. And second condition, when you take a vertex which is not yet processed, its neighborhood give a family of linearly independent vectors. Okay. So we have these two types of constraints. So the first constraint is this, so you need to realize these labels. But this gives a family of linearly independent vectors by the invariant. Okay. So you have a family of at most delta linearly independent constraints to satisfy. So the solution is an affine space of dimension t, the dimension of the full space minus delta. And on the other hand, you need to avoid, for every neighbor vj of vi, the vertex you are processing, you need to avoid a space of dimension at most delta minus 1 to be sure that the invariant holds. Okay? And now, if you count correctly, you show that indeed there is a vertex, a vector that satisfies these two constraints. You continue like that. Okay. And actually, this method is quite powerful because if we choose well the ordering for planar graphs, we can improve the order bound of 20. We can improve it to 12. Okay. So this uses a good ordering on the vertices. So intuitively, you want an ordering such that the degree of every vertex on its left is small, but you want something slightly stronger than that because you have the second constraint to satisfy. And so here I will not define it, but you can use an ordering that witnesses the fact that two strong coloring numbers of planar graphs are small. And anyway, it's just a good ordering that works well for this greedy algorithm. Okay, so to finish, just a few words about the complexity. So basically everything is hard, which is not very surprising. And this is a consequence of this structural result. If you take a graph and you subdivide every edge once, then the inversion diameter is the logarithm of the chromatic number plus 1, chromatic number of the original graph. Okay. And since computing the chromatic number is something hard, okay, almost all the problems are hard. And why is that? Just because when you look at the path of length 3, which is an edge subdivided once, or path of length 2, sorry, when you want to go from this orientation, so the two arcs in the same direction to this orientation, you and V, the extremities of this path, cannot be in exactly the same set of orientations, because otherwise you will always swap between this directed path and this one. Okay, so for at least one inversions, the U and V are separated. Okay. And so this gives a 2 to the T coloring if you have T inversions. And if you're careful with choosing the orientation of your graph, you can avoid the empty graph, the empty set. So this gives a 2 to the T minus 1 coloring. Okay, and the other direction is similar. Okay. And so computing the distances between two orientations is NP hard, even to determine if it's at most 2, and determine if it's at most 1 is easy. And determine the inversion diameter is also hard. But actually, to determine the inversion diameter is probably not in NP, because it's a problem of the form for every orientations, there exists a family of inversions going from one to the other. So it's probably P2 complete, which is a class in the polynomial hierarchy of the form for every there exists. Okay. So this is not a problem. Okay, and now to finish, a remark about some generalizations of this notion of inversion using this algebraic point of view and this definition of the inversion diameter. So now let K be an arbitrary field. For inversions, this will be F2, the field with two elements, but now we can look at it for any field. And Fk of G will be the smallest integer T, such that for every labeling of the edges with scalar from the field, you can find a family of T-dimensional vectors to put on your vertices, such that the labels on the edges are realized as scalar products of the endpoints. Okay. So for the field with two elements, this gives exactly the inversion diameter. But this makes sense in other fields, in any field actually. And here there is some remark. So if the field is finite, the behavior is the same as for F2, as the same as the inversion diameter, and this parameter is tied to the acyclic chromatic number and the star chromatic number. And the proofs are the same. Okay. But if the field is infinite, then this parameter is tied to the maximum average degree, which is the maximum average degree of a subgraph of G. Okay. And the reason for that is that you can just take an ordering in the greedy procedure to find the vectors. You can just take any ordering which shows that the degeneracy is small. Okay, so every vertex has a small number of neighbors on its left. Okay. And now the fact that in an infinite field you cannot cover the full space with finitely many proper subspaces shows that you will always be able to find a new vector to put on your vertex. Okay. And now to finish just a recap of the open problems. So first, about about making an analytic graph acyclic. So we have this estimation of the maximum value of the inversion number on n vertex over n vertex oriented graphs. So this is between n minus log n and n minus square root of n log n. But there is still a gap, okay, between the square root of n log n and this log n. It would be nice to know the answer. About making an oriented graph k-strong, a tournament k-strong. So as I mentioned earlier, we can always make a tournament on at least 2k plus 1 vertices k-strong using 2k inversions. And there exists a tournament that needs at least log k inversions. Here there is really a huge gap. We tried to improve it, but so far we didn't succeed. And on the inversion diameters, the maximum distance between two orientations of a given graph. For several class graphs, we don't know the exact value. So for planar graphs, we know that it's between 5 and 12. So the 5 is bound by a computer search. Okay, so I found the planar graph was inversion diameter is 5. Okay. I didn't mention it before, but for the tree width, we know that it's at most 2t using the same kind of greedy algorithm, adding vectors on vertices 1 by 1. Okay, and we have a construction achieving t plus 2. So here again, there is a gap. And we have the same kind of gap by a factor of 2 for the maximum degree. So we know that the inversion diameter is at most twice the maximum degree minus 1. And we have a lot of examples where it's at least maximum degree, where it's exactly the maximum degree. And we believe that this is always at most maximum. Okay. And that's all I have to say. Thank you.